Hi all, welcome back to our YouTube channel. In this video, we are going to cover another interesting cipher, that is Affine Cipher. So let's get started. In the previous video, we covered additive cipher and multiplicative cipher. So Affine Cipher is a combination of both these ciphers, that is, it contains addition and multiplication operation. Since there are two ciphers involved here, it uses a pair of keys K1 and K2. Let's look at the mathematical definition to understand it better. Similar to the previous ciphers, the key domain of the plaintext is a set of integers from 0 to 25, which we represent by Z26. Similarly, the ciphertext also contains the integers from 0 to 25, again represented by Z26. So in affine ciphers, we have two keys that are K1 and K2. Let's look at the key domain of key K1. So K1 consists of integers that are greater than 0 and less than 26 and satisfy a condition, that is, GCD of a and 26 is equal to 1, and this is represented by Z26 star. We have already covered this notation in the previous video. Do watch it if you haven't, link in the I button. So moving forward, this was the key domain of key K1. Let's have a look at the key domain of key K2. So K2 contains integers from 0 to 25, that is Z26. So we can observe that the key domain of key K1 is same as the key domain of a multiplicative cipher, and the key domain of key K2 is same as the key domain of an additive cipher, which implies that affine cipher is indeed a combination of additive and multiplicative cipher. Having understood this, let's have a look at the encryption and decryption algorithm of affine cipher. Let's start with encryption algorithm. So the encryption algorithm of an affine cipher is EK equal to P into K1 plus K2 mod 26. So we can see in the encryption algorithm, we first perform the multiplication operation followed by the addition operation. Let's look at the decryption algorithm of affine cipher. So the decryption algorithm is Tk equal to C minus K2 into K1 inverse the whole mod 26. Here K1 inverse is a multiplicative inverse of the key K1. So here we can observe in decryption, first we subtract, that is the opposite of addition, and then we multiply by the multiplicative inverse, which is the opposite of multiplication. So the order is reversed in decryption. Let's have a look how we can represent it diagrammatically. So here we have Alice with her plaintext and ciphertext, and here we have Bob with his plaintext and ciphertext, and both are connected via an insecure public channel. Now let's see how encryption and decryption can be represented. Since affine cipher is a combination of two ciphers, we will split the process of encryption and decryption into two parts. Let's start with the encryption. So the first step is T equal to P into K1 mod 26. You may be wondering what is this T. So T is a temporary variable which stores the value of the first step, which we'll use in the second step. So in first step, Alice multiplies the plaintext with the key K1 and applies the mod 26 operator to get the value of T. Now we go to the second step. Now this output is fed to the second step, which is C equal to T plus K2 mod 26. So this represents the addition operation, that is additive cipher. So we add K2 to the output of the first step and apply the mod 26 operator to get our ciphertext. Now this ciphertext is sent to Bob via an insecure public channel. Similar to encryption, the decryption is also divided into two parts. Let's have a look at the first part. So the first part is T equal to C minus K2 mod 26. So here Bob takes the ciphertext and subtracts the key K2 and applies mod 26 operator to generate the value of T. Now this value is sent to the second step, which is P equal to T into K1 of inverse mod 26. So here Bob multiplies T with the multiplicative inverse of key K1 and applies the mod 26 operator to generate the plaintext. So we can see in encryption, we first apply the multiplication operation followed by addition operation, whereas in decryption, we first apply subtraction, which is the opposite of addition, followed by multiplication operation. So the orders are reversed in decryption. And in cryptography, this is a general rule applied in any combination cipher, that is, the order used in encryption is reversed in decryption. So the last operation in encryption becomes the first operation in decryption, and the second last becomes the second, and so on. Also note that both these keys K1 and K2 are shared via a secure key exchange channel. So both these keys should be exchanged in a secure way. So this was a diagrammatic representation of affine cipher. Let's take an example to understand it completely. So here the example is encrypt the message hello using Affine Cipher with key pair 7,2 and again retrieve the plain text from the ciphertext. So let's solve this problem. So first we have plain text which is hello, key 1 is 7 and key 2 is 2, and the encryption algorithm we have is C equal to P into K1 plus K2 mod 26. Let's construct a table to calculate the value of C. So the first row is P. So we have H, E, L, L, O. Then we have the integer value of P. Let's call a mapping table back for a reference. So here H represents 7, E represents 4, L represents 11, again we have L, so 11, and O represents 14. The next step is P into K1, that is we multiply K1 with all the above values. So 7 into 7 gives us 49, 4 into 7 is 28, 11 into 7 is 77, again 77, and 14 into 7 gives us 98. The next step is P into K1 plus K2, that is we add K2 to all the above values. So 49 plus 2 gives us 51, 28 plus 2 gives us 30, 77 plus 2 gives us 79, again 79, and 98 plus 2 gives us 100. The next step is we apply the mod 26 operator. So the first value is 51. We know that 26 2s are 52. So if it was 52, then the modulus would have been 0. It is 1 less, so the modulus is 25. Next value is 30. So 30 mod 26 gives us 4. The next value is 79. 26 into 3 is 78. So it is just one value more than it. So we have 1. Same goes for the next value. And the next value is 100. So 26 into 3 gives us 78 and 26 into 4 gives us 104. Since 104 is greater than 100, we have to take 78. So 100 minus 78 gives us 22. And in this way we can calculate the modulus manually since the number are small, and if they are big, we can always rely on the scientific calculator method which I've already discussed in the modulo operator video. Link in the I button, do check it if you haven't. Coming back to the topic, the final step is C, that is the ciphertext. So again referring to the mapping table, 25 represents Z, 4 represents E, 1 represents B, again we have B, and 22 represents W. So the ciphertext is ZEBBW. So we have successfully completed the encryption process. Now let's apply the decryption process to retrieve a plaintext back. So the decryption algorithm used in Affine Cipher is P equal to C minus K2 the whole into K1 inverse the whole mod 26. So we can observe that we require K1 inverse here. So we will calculate K1 inverse using the extended Euclidean algorithm. We have already covered how to calculate multiplicative inverse using the extended Euclidean algorithm in our previous videos. Link in the I button. Coming back to the topic, so here A is the value of K1, that is 7, and B is 26. We will construct a table to find the multiplicative inverse of key K1. So the columns we have here are Q, A1, A2, A3, and B1, B2, B3. The initial value of Q is null, A1 is 1, A2 is 0, A3 is the second number, that is 26, and B1 is 0, B2 is 1, and B3 is 7, that is the first number. So we will calculate the next value of Q. So the formula for Q is the floor of A3 by B3. So it is floor of 26 by 7. So if we divide 26 by 7, we get 3 point something something, and then we apply the floor operation, so we get the value as 3. Now let's calculate the values of A. So the values of A are the previous values of B. So your A1 is 0, A2 is 1, and A3 is 7. So we have 0, 1, and 7. Now let's calculate the further values of B. So B1 is 1 minus 3 into 0, which gives us 1. B2 is 0 minus 3 into 1, which gives us minus 3. And B3 is 26 minus 3 into 7, which gives us 5. Let's continue the iteration further. So the next value of Q is floor of 7 by 5. So if we divide 7 by 5, we have 1 point something, and then we apply the floor operation, and we have the value as 1. The further values of A are the previous values of B. So A1 is 1, A2 is minus 3, and A3 is 5. Now let's calculate the further values of b. So b1 is 0 minus 1 into 1, which gives us minus 1. b2 is 1 minus 1 into minus 3, which gives us 4. And b3 is 7 minus 1 into 5, that is 7 minus 5, which gives us 2. Since b3 is not 1 or 0, we will further continue the iteration. Let's calculate the next q value. So it is a floor of 5 divided by 2. So if we divide 5 by 2, we get 2 point something something, and then we apply the floor operation, so we get the value as 2. The values of a are the previous values of b. So a1 becomes minus 1, a2 becomes 4, and a3 becomes 2. Let's calculate the further values of b's. So b1 is 1 minus 2 into minus 1, that is 1 plus 2, which gives us 3. b2 is minus 3 minus 2 into 4, that is minus 3 minus 8, which gives us minus 11. And b3 is 5 minus 2 into 2, that is 5 minus 4, which gives us 1. We can see b3 is 1, so we stop the iteration. Since b3 is 1, it indicates that mi exists. And what is that mi? It is the current value of b2, that is minus 11. So k1 inverse is minus 11, but we know that the key domain of k1 is z26 star. So we have to apply the mod operator. So minus 11 mod 26. Since the number is negative, we just add 26. So minus 11 plus 26 gives us 15. So we have got the value of k1 inverse, which is a multiplicative inverse of key k1, which is 15. So now we have everything for decryption algorithm. So let's decrypt the ciphertext. So here the ciphertext is ZEBBW, k1 inverse is 15 and k2 is 2, and the decryption algorithm is P equal to C minus k2 the whole into k1 inverse the whole mod 26. Let's construct a table to find the plain text. So the first row is C. So we input Z, E, B, B, W. The next step is the numerical value of C. Let's call a mapping table back for a reference. So here Z represents 25, E represents 4, B represents 1, again we have B, so 1, and W represents 22. The next step is C minus K2, that is we subtract K2 from all above values. So 25 minus 2 gives us 23, 4 minus 2 is 2, 1 minus 2 is minus 1, again minus 1, and 22 minus 2 gives us 20. The next step is C minus K2 into K1 inverse, that is we multiply K1 inverse with all the above values. So 23 into 15 gives us 345, 2 into 15 gives us 30, minus 1 into 15 is minus 15, again minus 15, and 20 into 15 gives us 300. The next step is to apply the mod 26 operator. Since some of the numbers are big, we will use a scientific calculator for our convenience. We have already covered how to calculate modulus using a scientific calculator in our modular operator video. Do watch it if you haven't, link in the I button. So let's calculate 345 mod 26. So the first formula we use is A divided by B. So the value of A is 345 and the value of B is 26. We use the S2D button to get the value of X, which is 13. Now we will use the second formula, that is A minus X into B. So the value of A is 345, value of X is 13, and value of B is 26. So we get the value that is 7. So 345 mod 26 gives us 7. The next value is 30. So 30 mod 26 gives us 4. The next number is minus 15. Since it is a negative number and less than 26, we just add 26. So minus 15 plus 26 gives us 11. Again we have 11. Now let's calculate 300 mod 26 using the scientific calculator. So we'll use the upward button to use the first formula, that is A by B. So here the new value of A is 300 and the value of B is 26. We use the S2D button to get the value of X, that is 11. Now let's use the second formula. So here the value of A is 300, the value of X from the previous step is 11, and value of B is 26. So we have the value as 14. So 300 mod 26 gives us 14. The last step is P, that is a plain text. Let's call a mapping table for a reference. So here 7 represents H, 4 represents E, 11 represents L, again we have 11, so L, and 14 represents O, and hence the plain text is hello, which was the original plain text. So we have successfully retrieved our plain text using decryption algorithm. So with this example, I hope you're clear with all the concepts of Affine Cipher. So that's it for the video guys. Thanks for watching the video, and if you have any doubt, please do let us know in the comment section below, and if you have found the video helpful, do like and share the video with your friends and subscribe to Be the Best channel for more such videos. Meet you in the next video of the CSS series. Bye bye.